Hi, this video we're going to be talking about polytropic process. So polytropic process is basically during the expansion and compression process of gases. They said the pressure P and the volume V, they're related to this polytropic because there's an N as um, exponent here. A polytropic process, it's a pressure volume relationship. So I'm going to write it down here. So pressure and volume, they follow this relationship. And be aware here, N exponent and C both they are equal, they are constant, they are constants, right? Now, knowing that, I want to specify here N doesn't have to be a integer. It can be a decimal, like for example 1.2, right? Okay, I want our mind not be limited to just integer. So now let's look at the boundary work for polytropic process. We want to find the formula for that. We start with the governing equation. It's going to be PdV, right? From state 1 to state 2. Then, just like how we did to find ideal gas as a thermal process, we substitute to P. Here, we're going to do the same thing. Because it is polytropic process, they follow this relationship. So pressure is just going to be equal to C over Vn, and it's C times V to the negative n. So substitute that in this equation right here. We have this. And again, C here is constant. We can take C out of the integral, and then we will have just V negative n dV. Now, how do we integrate that? How do we integrate this one? So there are two scenarios. First, I want you to think about if n here is equal to 1. What do we have? That's possible, right? Because n can be any constant. Then this boundary work is going to be equal to C dV because n equal to 1. Does this look familiar? This is what we talked about last time for boundary work for isothermal ideal gas, right? So if we were trying to integrate that, that'd be natural log V2 over V1. And then our C here is a constant as PVN, and our N here is equal to 0. So our C just going to be equal to P times V natural log V2 over V1. This is exactly what the expression we had last time. So this scenario, when n equal to 1, for this polytropic, we know this is going to be isothermal process. And it's ideal gas. Okay. But that's not our focus so far, because there are so many n that can be any other number except as 1, right? So when n is not equal to 1, how are we going to integrate this? Right? So a quick review on calculus to help us understand that. Now let's see, what is integration of, let's see how example like x dx. That's going to be x squared over 2, right? How do we do that? We're going to add this exponent, add 1 to it, and then divide this new exponent. That's how we're going to look at this. We are going to, when we are trying to solve the boundary work, it's going to be C V negative n dV. Let's copy that down. So when we're trying to integrate that, we're going to add 1, and we're going to divide by this new exponent. That's how we integrate this. And here it's going to be our V1, and this is going to be our V2. All right, so when we get this, and we can make a little bit streamline, a bit looking. So here we will have 1 minus n. and our C. So C here, we're going to first we're going to replace C because C is equal to P times Vn. So when we times V2, we're going to see C here is going to be P2 V2 power of n. So C have to times V and V2 1 minus n. But when we substitute V1 in there, and we're going to have C times V1 to the power of 1 negative n. But here C, I'm going to use P1 V1 to the power of n, right? Why can we do that? Because they all satisfy this equation. I can see P1 V1 to the power of n equal to C. Also, I can see P2 V2 power of n to the C. Okay, so now this is our C. This is also our C. Then we're going to times V here. It's V1 1 minus n. All right, so that's the math behind it. Now let's continue, see if we can clean this up. So then we have P2 and V2, and then when we add times this together, we're going to have, so when we times those two together, you add exponent together, so it's n plus 1 minus n, so it's power of 1. Then the second one, when you have P1 V1 and the same base, you just add exponent together, so it's n plus 1 minus n, it's also power of 1, right? So we get this very sleek answer here. That's going to be our boundary work. And what's the condition for this? This is for polytropic process. And also when n is not equal to 1. Because when equal to 1, this equation won't work, right? So with this, we wrap up for this video about polytropic process. PVN equal to C, and also you can use for different state P1 V1n equal to C, etc. And for the boundary work, we calculate boundary work is this equation P2 V2 minus P1 V1 over 1 minus n. That's when n not equal to 1. When n is equal to 1, it's basically the isothermal ideal gas situation. That's all for this video. See you next time. Bye.